looking at runout tolerances. Everything you wanted to know but was afraid to ask. So in here, learn how to apply it, interpret it, different methods that are used, be able to describe the features that we inspect for runout, and apply them or interpret them, the form tolerances, when we use an independency, which is basically puts rule number 1 to the side and allows us to control it with our form, okay, independent of the size. So runout, used to control surfaces that are constructed around an axis or perpendicular to an axis. So you can have a wobble effect as well as cylindrical effect. It's alright, I'll edit that out. So we control circular elements, one circular ring around a surface, or we can also control the cumulative effects, because straightness, coaxiality, angularity, taper, or profile of a surface can all affect runout. So if we check for runout, sometimes it's also checking for those at the same time. But we can also specify those combinations. So it's always, regardless of feature size, the amount of runout, because we're checking how much it's out of shape, if you want to think of it that way, how elliptical it might be, or bumpy, but it's basically how it's shaped with an axis. So it doesn't matter if it's 10 inches or plus or minus 10 thousandths or whatever it is. We're checking for how close it is to the axis. Okay, so we connect it with the feature control frame to the surface using a leader, and then we can use multiple leaders. So there's two types: the total runout, which is all over the surface, okay, around. Kind of sounds like, cylindricity, but this is based on the amount of it runs out, not all of its shape. Okay, we're just interested in how much our indicator changes. Circular runout is just in one circle, maybe in two places. So your runout tolerance uses this little arrow, or if it's total runout, uses this double arrow. And they can be blocked in, or they can be open. So circular runout controls circularity and coaxiality when it's applied to surfaces around either perpendicular or an axis. We can use it to control what we call a wobbling motion, okay, that we're watching for, where it wobbles side to side. We can control a datum. Controlling datum is verified before checking the other surfaces. So we can have a runout that's controlling a datum, and it's always regardless of material boundary. So circular runout is measured by a full indicator movement. Here's your little indicator. I showed you some of those over there in the metrology lab. The little shaft moves in and out, makes the dial move, and so we look for this full indicator movement, FIM, and we rotate it in a circular motion. If we can hold it on an axis, that's good. Point to point, side end to end. We rotate it a full 360. So here's circular runout, 0.15 millimeter, based on the X. So X is actually our 30 millimeter diameter and that's actually datum X. You know, no basic dimension, no control on it. That establishes the axis. So we may actually hold on to this like a drill chuck does, you know, a 3-jaw chuck. Okay, we may actually hold on to the end of this, and that creates the axis. Then we apply the indicator and to a perpendicular angle. So if it's on a surface, a conical surface like this, then our indicator has to be perpendicular to the surface. So it's a total tolerance. So we're looking for how much the little dial moves, total amount, and each element must lie within full indicator movement, each circular element. But once again, we're checking in one place, and where we point with our arrow, that's where we want the inspector or tool maker or whoever to check the part. Alright, total runout, it controls the combined variations of all these. Okay? So it's circularity, straightness, coaxiality, angularity, taper, and profile when applied to surfaces constructed around and at right angles to a datum axis. So we're rotating it 360, and then we move the indicator back and forth. Alright, takes a little bit longer to check it. Now notice right here we have a very tiny control, 0.08 or 0.08 of a millimeter on the face of this truncated cone, this flat area here. So we're actually looking for this wobble on the end here. It can also control concavity and convexity when applied to surfaces perpendicular. So that's what you're doing here. It's always regardless of material boundary, and the tolerance zone encompasses the entire surface. Alright, now applying a runout to a portion of a surface is simple concept. We essentially draw a chain line, a thick center line, and apply basic dimensions to it. This is where maybe a bearing fits, something critical fits here. So the rest of it is controlled by other means, but this area right here, we are controlling the entire surface, total runout. Okay, applying a runout to a datum surface and a datum axis. So we place datum separately in a feature control frame, okay, like so. And the profile must be within the specified geometric tolerance when the part is mounted on the datum surface and rotated 360 degrees. So the surface is this 20 millimeter cylinder out here, and the datum X is of course perpendicular to the axis. So a fixture will be created that will hold this part and hold it here, and then the runout, total runout, is checked here, and then on the cone just circular runout, or just in one element. Now if we want control, applying runout control to a datum, the center datum feature symbol below the feature control frame, okay, we center it, or we connect datum feature symbol to the leader shoulder. So it's kind of a interesting application of our datum feature symbol. Okay, putting it right on the shoulder of the arrow. This is the preferred method here. So it's telling us that this runout is actually the datum. Now we have combinations. Here we got profile and circular runout. Now there's many combinations we could have, but if we have a particular profile we want controlled, Then also we can come back in. See, this is 0.2 of a millimeter for profile, but then the runout is a tighter control, so that's possible. Then runout and cylindricity can be combined like this. Since they're both based on an axis, it makes sense to combine them. We're showing the circular runout in referencing C and D. So we're going to hold this and this is our datum and then check for runout, which also we're going to check for cylindricity. Okay, which means we check circular runout right here at this point, and then the cylindricity comes in, and it's a tighter control. About 1/3 of the tolerance is allowed along the whole surface. So at any one point, it can't wobble at one point. Okay? Wobble is allowed, but the cylinder surface must be within a zone that's 0.05. Then there's independency. Form control then is independent of the size tolerance and should be added to the feature. So this is an independency symbol. The circle I says that the form, rule number 1, does not apply. Okay, so that this runout can exceed and go outside of the size of the object. Remember, rule number 1 says it has to be contained within the feature of size. So if we put a circle I out next to it, we basically turn off rule number 1 to allow us to check the entire surface, and normally this is used on a long part, okay, where we got a tight control over a long surface. We don't really know how long this part is, but it's 5 millimeters here, so it's not all that long, but it's long in proportion to the datum that is controlling, okay, or that it's referencing. So in review, runout is a combination of geometric tolerances used to control the relationship of one or more features of a part to a datum axis. The fundamental difference between how circular runout and total runout are established. Circular controls a singular circular element. Total runout encompasses the entire surface 360 degrees. What does the chain line represent? It's where the runout tolerance is located. Runout is always controlled on regardless of feature size.